All right, so this is going to be a video about finding volume, and basically the way we're going to be finding volume is when you have a function. So I have a picture right here that's going to kind of show this a little bit easier. But imagine you have some function here, just some arbitrary function, a region in the xy plane, and they kind of tilted here to kind of show it three-dimensionally. And imagine if you took that shape and you revolved it around the x-axis. So this is like kind of partly revolved around, but now imagine if you revolved it all the way around. So you took that original function that we have right up here and you revolve it around, and you're basically just making this weird cylindrical type of shape. And if you notice, it's just a bunch of circles. If I wanted to, I can draw in infinitely many circles here that are just kind of stacked up, horizontally with each other. And you can add up all those circles, all the areas of those circles, and you're adding another dimension to it. And since you're adding another dimension to it, a circle with area is two-dimensional, you're adding another dimension, it becomes three-dimensional because you added that other dimension to a 2D shape. So we have a 2D circle right here. You can kind of see one right here as well. And if you add those all up, so essentially what you're doing is adding up or integrating. Integrating means putting things together. All the areas of a circle with respect to x. Okay, it's with respect to x because we're doing it around the x axis here. Well, the area of a circle is just pi r squared. Okay. Well, the radius, if you just take any of these circles, there's infinitely many of them. Let's just do the one on the end, kind of to make it a little bit easier. The radius of this circle is the y value. However high it goes up to this y value, this distance right here, is whatever the y value is. Well, in this case, the y value is whatever the function is. So if we wanted, we can rewrite this. We can put the pi in front because it's a constant. The r is just whatever the y is. For any of these circles, it's always just going to be the y. The y's are different because the function is different at different x's for this one. So essentially, we can say the r is the y. So we can just say the y is the f. We can just square the function with respect to x, and we're integrating that from a to b. Okay, I could have put a to b in all these. But you're basically just adding up from a to b all those infinitely many circles that are between that interval from a to b of the function squared. It's the radius squared of that circle. And that's basically how we get to our first formula for volume, called disk method, which is this right here. This will get you the volume of any solid of revolution around the x-axis. And it is important to note, we could revolve around the y-axis if we wanted. We would just have to change all those x's into y's. It's the same exact formula. It's called disk method because essentially it's just a bunch of disks, a bunch of circles that are stacked horizontally, essentially, and you're just adding up all those circles. But this is super important, this disk method formula. This is what we're going to use to find the volume of these solids of revolution. Okay. To kind of seal this in a little bit more, let's work out an example. So right here it says find the volume of the solid of revolution formed by revolving the region between the graph of the function f of x and the x-axis over the interval from 1 to 2 around the x-axis. Now, what I like about this graphic here is it actually shows the original graph. So we have the original graph right here, and then we're revolving it around the x-axis, and you get this shape right here. Okay. Now there's a volume to that shape. Now the old school way of finding volume, like in a geometry class, is you figure out what the shape is. What is the shape? Is it a pyramid? Is it a cylinder? Is it a cone? And then you just use some formula. Well, with this, there is no formula for this. I mean, what shape is this? The shape is defined by whatever the f of x is. So in this case, we can't just find a formula. We have to use that integration, that disk method, to basically figure out the volume of this weird shape. Now, why is this important? Okay, you don't need to know this for the class, but I just like kind of showing where things come from and then why they're important. There's a lot of constructing of objects that have weird shapes. Not everything is a perfect square or a circle or a sphere or whatever it is. Sometimes it's just weird shapes. I mean, just look around you, you'll see a bunch of weird shapes that have some volume. Well, we are getting to, especially with our manufacturing processes getting better and better, 3D printing, that sort of thing. It's like all this stuff is created with math. A lot of the objects around us are created with math because they're having machines do it, they're having robots do it, they're having some manufacturing process do it. So it makes sense to be able to figure out the volume, the amount that you need, whatever you're creating, using math, because that's the language that computers speak in. It just kind of all makes sense of why we're doing this. Now, granted, computers do all this stuff. We're doing this by hand, but it's a math class. I have to teach it this way. But that's kind of why this stuff is so important. This stuff was invented, 400 years ago or something like that, and it's just crazy to think that, like, all that stuff that was created a long time ago, they never even realized what we could really do with all of that stuff, and just how much it's used nowadays. But either way, let's try to find the volume of this shape here. All right, so the volume is going to be, following that formula, it's going to be pi times the integral, in this case from a to b is 1 to 2, okay, as you can see it's integrating from 1 to 2. And it's whatever the f of x is squared. So this is just x to the negative 1 power. So I'm going to square it, so it's going to be x to the negative 2 power. That way we can use reverse power rule on this. It's nice and easy to work with. Okay, first thing we're going to do is do the antiderivative of this. So we're going to add 1 to the power and divide by that. So it's going to be x to the negative 1 divided by negative 1. So I'm just going to put a negative in front to make my life easier. And we plug in the 2, we plug in the 1, and we subtract. So that's what we're going to do here. Don't forget that pi in front. That's a common thing that people will forget. All right, I'm going to pull that negative out just to make my life a little bit easier. So it's negative pi. And we're going to plug in the 2, so it's 1 over 2, minus, plugging in the 1, it's 1 over 1, which is just 1. So you have something like that. You can distribute the negative if you want, just to make your life a little bit easier. Doesn't matter. This problem is pretty easy, pretty straightforward. And again, you're going to see problems like this on your quiz. I'm not going to try to make this overly complicated where you have to use substitution or integration by parts or anything like that. A lot of these tend to be pretty straightforward. Usually reverse power rule, stuff like that. Anyway, let's keep going here. So 1 plus negative 1/2 is just going to be 1/2 times pi is pi over 2. And that is the answer for this problem. So the area of this shape right here is pi over 2. Okay, and the formula that we used was that disk method formula. Hopefully that makes sense. Pretty straightforward. All right, the next type of volume problem that we're going to be doing is called washer method. And the reason it's called washer method is if you kind of think of a washer like the metal washer that's used to, it's usually used in like tightening of certain things. All right, so washers are basically these metal, discs that, if you notice, there's a certain volume to this. It'd be a cylinder, but there's a hollowed out section of that, and you can find the volume of it. Essentially with washer method, it's the same as disk method, only there's going to be a negative space. In the example that we have right here, you can kind of see that. So we have some, shape right here, this area, and then we're revolving it around the x-axis. Well, there's going to be this negative space in between, which you can see right here. It says right here with a cavity. So there's this negative, hole right here, but it kind of forms like a donut. You have to kind of imagine that in your head. That's why it's called washer method. It's basically disk method, just like before, but there's a part where you're subtracting it out, that minus g of x squared. And g of x, f of x would be the outer radius, the inner radius would be g, and you're basically subtracting off that other shape. Okay, so that's washer method. Same exact thing as disk method with just that subtraction part. To kind of seal this in, let's look at an example problem. So this problem here says find the volume of a solid of revolution formed by revolving the region bounded above by the graph of y equals x. So here's y equals x right here above, and then the bottom part below the graph is 1 over x right here. And if we revolve around right here, you're going to have this negative space right here, essentially, from the entire thing. I mean, this picture obviously shows it a lot better than what I drew out. But there's a negative space in this, so it's it's going to be a weird donut shaped kind of thing, some hollowed out part, and we're trying to find the volume of that. Okay, so let's do that using that formula. So it's going to be pi, we're going from 1 to 4 on this, okay, x squared minus, now it's 1 over x, I'm just going to write x to the negative 2 again, just so I can use reverse power rule. Okay, from here we're going to do the antiderivative of each of these terms. So it's going to be 1/3 x cubed minus negative x to the negative 1. Okay, we just did this problem, so it's the exact same antiderivative. And we're integrating it from 1 to 4. Keep that pi out in front here. Plugging the 4 in. Okay, 4 to the third is going to be 64, so we're going to have 64 over 3. Make this a little easier. Plus 1 over 4. I'm going to put parentheses on that just to kind of show the grouping a little bit easier. Minus, okay, plug a 1 in, you're going to have 1/3. Plug a 1 into the other one, you're just going to have 1. So you'll have something like that. All right, from here, we're going to distribute the negative here just to make our life a little bit easier. And just to have common denominators on all these, let's just do, we'll just do 12. So that 64 times 4 is going to be 256 divided by 12. Plus, again, we want a denominator of 12 here, so we're going to put a 3 there. plus negative 4/12. Multiply the top and the bottom by 4 there, and then minus 12 over 12. All right, and if you sum those up, you're going to get 259 minus 4 is 255, minus 12 is 243. So you're going to have 243 pi over 12, which can simplify. We can divide the top and the bottom by 3, so you have 81 pi over 4, and that's the answer. So that's volume using disk method and washer method. It's pretty straightforward if you follow that formula. If you have any questions about anything in this video, let me know.